Okay, now we're looking at learning target number 3, and this is about moment of inertia. Okay, and we've talked about inertia before, and that's back in a really early unit. Inertia is a property of matter, and it's how matter resists change, and we have to apply a force in order to get an object moving or to make it stop, and it's going to resist that change. And so moment of inertia is very similar. It's resisting rotation. Okay, so the more torque and force required to cause rotation, the greater the resistance to that rotation, and that resistance we call moment of inertia. Now, we're not going to look at, we're not going to use equations. We just need to have a conceptual understanding of moment of inertia. The base idea here is that different shapes, different distribution of mass has different moments of inertia. Okay? And the main idea behind moment of inertia is if we can get the mass to be close to the axis of rotation, then we have less inertia. It's easier to spin and rotate. So let me give you an example that I like. Here's the pen, and if I make my axis of rotation right down the center of the pen where the ink is, and I'm rotating around that axis, the mass of the pen is so close to the axis of rotation. And so the moment of inertia, the inertia is small. It's easy to spin this pen like this. It doesn't take much torque to do so. But if I move the mass away from the axis of rotation, if I change...
Alondra, Vasquez, could you come to the front office, please? Alondra, Vasquez, come to the front office.
If I change my axis of rotation to be the end of the pen, and so I'm rotating here now. I'm rotating like this. This is a lot harder to do, because if this is my point of rotation, look at all this mass that is so far away from that point of rotation. So the more mass that you have further away from that point, the harder it is to rotate the object. Okay, the greater resistance to that rotation. We see this pretty clearly with ice skating. If you've ever watched Olympic figure skating, and they're out in the middle of the rink and they have their arms out and they're spinning around, and they're spinning relatively slowly, and then they bring their arms in and they start spinning much faster. Okay, and that's the only thing that's changing, is they're taking their mass being further from the axis of rotation to being close to the axis of rotation. And so we have less rotational inertia here. So it's easier to spin, and so they speed up. Okay, now let's talk about center of mass and stability. So, center of mass. The point an object, so the point on an object that can move in the same way that a point particle would move. Like, where on the object would it act the same as if we took all the mass and put it in that place? Okay. Now, I really like this example. I really think it clears up this idea. The center of mass of this bat, like if we throw a bat, it's going to follow a parabola. Now, that doesn't mean that the rest of it follows the parabola, but the center of mass will make a parabolic motion. It acts like a point mass, and so then that must be the center of mass. Now, and we'll talk about this here in a moment, there is a way of creating stability depending on the location and alteration of the center of mass. Okay? So the center of mass is a single point on the bat that traces the parabolic path of the bat. So if I apply a force, okay, like I push on the box, and so that force is going to create a torque. We are some distance away from the point of rotation. Okay, the force is being applied and it's causing a torque, and so it's going to cause it to rotate. Now, there is also another torque, and that is the mass, the weight of the object is going to pull it back, right? If I push this box and then I let go, it falls back. And that's because the center of mass is not at the center of the rotation. It's not, it's rotating around like maybe the corner here. And so the center of mass is not at the point of rotation, and so it has a force that's perpendicular component, and that's going to cause a torque going back the other way. Now, if I push this box to the point that the weight is now directly above that stability point, that support point, or the point of rotation, then the torque will equal 0, right? The R component would be 0. And this is this is kind of that like teetering point. So at this point, when this happens, the only torque acting on the object is from the force. And so that must mean that it's going to continue to rotate and fall over. And once that center of mass passes that point of support, once it passes the base of the object or the point of rotation, now it's on the other side of that point of rotation, and so it's going to cause it a torque to go this direction. So now we have 2 torques causing it to fall over. Okay? So there's the science behind it. The main idea, maybe write this at the bottom, the main idea is when the center of mass moves beyond the base of the object, that's when the object's going to fall over. Okay. So if we look at these cars here, they're at the same angle. Okay? 2 things that are helpful to these vehicles. First, if we lower the center of mass, okay, so if the center of mass is here, but we lower it, that helps with stability. Okay, so lowering the center of mass, that's the first part of it. The second one is to increase the area of the base, like the length between wheels is larger typically on these sports cars. Their wheelbase is larger than like on a Jeep, and they're kind of this aerodynamic shape, and so it kind of forces that center of mass to be lower, so we gain a lot of stability. We don't see these cars flip over as often, but we see it happen a lot with Jeeps because their center of mass is higher and then maybe the wheelbase is smaller. And so when these 2 vehicles are set at the same angle, do you see how this torque of the center of mass is stable? It's not beyond the base of the object, but this one is unstable. It's beyond the base of the object. So this car is going to fall over, but that one's not. Okay. So that's the idea behind moment of inertia, center of mass, and stability.